All right, let's take a look. Plus minus emission spectra. What wavelength should the astrophysicist look for to detect a transition of an electron from n equals 7 to the n equals 3 level? This is a Reisenberg formula equation. There are two different forms we give you in lecture. The first one, by way of review, is delta E for the difference in energy is equal to the opposite of the Reisenberg constant times the inverse of n squared final minus the inverse of n squared initial. The other version, and for this version, the Reisenberg constant is going to have energy in joules, and that's going to be 2 point, let me erase that 2, it got really sloppy there. 2.179 times 10 to the negative 18 joules. The other version is the inverse wavelength, and that's an important thing that causes a lot of people trouble, is that's not the wavelength, but the inverse wavelength is equal to the Reisenberg constant, and here they forego that plus sign, that negative sign, and it's 1 over n squared final minus n squared initial. Okay, if we look, they're asking for wavelength. So we're going to want to use the second version of the formula since they're asking for wavelength. And for this second version, the Reisenberg constant has some really funky units. 1.097 times 10 to the negative second, not nanometers, but inverse nanometers. So this is the version of the equation we're going to want to use. They gave us the n equals 7 and n equals 3 already, so it's a matter of plug and chug. So let's chug and plug. We have our inverse wavelength equal to that RH constant, 1.097 times 10 to the negative 2 inverse nanometers times the final energy state, which is 3, so it's 3 squared, minus the initial energy state, which is 7 squared. Let's do some quick math here, and let's resolve what we've got in here. We've got 1 over 9 minus 1 over 49, which is going to be equal to, punch it into our calculators, 9 inverse minus 49 inverse equals 0.09070249 is what your calculator tells you, but that's okay. We're then going to multiply that by 1.097 times 10 to the negative second, or times that RH constant. And that gives us an inverse wavelength of 9.9501133 times 10 to the negative fourth inverse nanometers. Something that's important to realize, by the way, is your 3 and your 7 are exact numbers. So your sig figs is actually going to be dictated by the 4 sig figs that you have there, in case you were curious. Here's where a lot of people get it wrong. If this was a multiple choice exam, what you see right here would be choice A. However, if you look at this formula, you're not solving for wavelength in this formula, but inverse wavelength. And you want wavelength. So how are you going to solve that? Well, to get the inverse of the inverse, you're going to have to take the multiplicative inverse of both sides of the equation. So I'm going to raise both sides to the negative 1 power, or take the multiplicative inverse of both sides. And that's going to give me a wavelength value of 1.005 times 10 to the third nanometers, because we've inversed that unit. Or if you'd rather, 1,005 nanometers. And that's that. I just noticed that there was a cutesy finishing step here at the end, because I'm happy with nanometers, and that would be a usual unit for light. They are asking for meters, so we're going to have to do one last cutesy finishing step so that you can get the correct answer in Mastering Chemistry. We have nanometers, 1.005 times 10 to the third nanometers. You want to convert to meters. Place nanometers where they cancel out. You've memorized 10 to the 9th meters is equivalent to 1 nanometer. So 1.00, whoa. Sorry about that. 0.005 times 10 to the negative 6 meters. By the way, they only give it 3 sig figs when it really should have 4 sig figs. So they're actually looking for 1.00 times 10 to the negative 6, just because the graduate student messed up.